Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Scanning Electron Microscope SEM from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. First, we'll differentiate between scanning electron microscopy and optical microscopy. Second, we'll discuss the advantages of SEM and its applications. Third, we will get to know about thermionic and field emission gun. Lastly, we will discuss about the significant role of condensed and objective lens in the resolution of SEM. So students, let us start with a basic introduction about the module. The Scanning Electron Microscope SEM uses a focused beam of high energy electrons to generate a variety of signals at the surface of solid specimens. So here the signals that are derived from electron sample interactions, they reveal information about the sample, including the external morphology, texture, chemical compositions and crystalline structure, and the orientation of materials which are making up the sample. So in most applications, data are collected over a selected area of the surface of the sample and a two-dimensional image is generated that displays spatial variations in these properties. So areas ranging from approximately 1 centimeter to 5 microns, in which they can be imaged in a scanning mode using conventional SEM techniques, where the magnification is ranging from 20x to approximately 30,000x, spatial resolution of 50 to 100 nanometers. So the SEM is also capable of performing analysis of selected point locations on the sample. This approach is especially useful in qualitatively or semi-qualitatively determining the chemical compositions using EDS, crystalline structure, and crystalline orientation using EBST. Optical microscopy versus scanning electron microscopy. So as you can see students over here, there are two images of the same object using OM optical microscopy, where there is a small depth of field that is low resolution, and using scanning electron microscopy SEM, where there is a large depth of field leading to high resolution. So now let us discuss the scanning electron microscopy SEM. We will be discussing first what is a SEM, the working principles of SEM, their major components and their functions, electron beam specimen interactions, interaction volume and escape volume, magnification, resolution, depth of the field and image contrast. So we have four kinds of spectroscopy spectra, that is First is energy dispersive X-ray spectroscopy, EDS. Second is wavelength dispersive X-ray spectroscopy, WDS. Third is orientation imaging microscopy, OIM. And lastly, we have X-ray fluorescence, XRF. Now let us start with what is SEM. So as evident from this figure, SEM consists of a sample chamber and a column and the TV screen which is being interfaced with our system, and SEM is designed for direct studying of the surfaces of solid objects. Scanning electron microscope SEM is a microscope that uses electrons rather than light to form an image. And as we know that there are enormous advantages to use the SEM instead of OM. So let us discuss the advantages of using SEM over OM. Magnification depth of field resolution. For OM, it is 4x to 1000x, that is 15.5 micron to 0.19 micron, approximately 0.2 microns. For SEM, 10x to 3 into 10 to the power 6x, 4 mm to 0.4 microns, and 1 to 10 nanometers. Now here SEM has a large depth of field which allows a large amount of the sample to be in focus at one time and produces an image that is a good representation of three-dimensional sample. So the SEM also produces images of high resolution, which means that close features can be examined at high magnification. The combination of higher magnification, larger depth of field, greater resolution, and compositional and crystallographic information makes the SEM one of the most heavily used instrument in research areas and industries, especially in semiconductor industry. The main applications of SEM. So we have categorized the main applications into 4 categories. First is to study topography, which means the surface features of an object and its texture, that is hardness, reflectivity, etc. Second is to study the morphology, that means the shape and the size of the particles making up the object. Let us say for an example that is strength, defects in IC and chips, etc. Third one is to study the composition, that means the elements and the compounds that the object is composed of and the relative amounts of them, melting point, reactivity, hardness, etc. The last application is to study the crystallographic information, means how the grains are arranged in the object, which may affect the conductivity, electrical properties, strength, etc. So let us see a more detailed look inside a scanning electron microscopy. So this figure shows the principle of scanning electron microscopy, where we have an electron gun in order to produce the electron beam, which passes through the condenser lenses in order to focus the beam, and then it is focused on probe forming lenses, and then through BSE. BSE is what? BSE is backscattered electrons. And then SE are the secondary electrons which are focused onto the specimen. Now onto the specimen, we have this whole morphology of the specimen into our computer, which is being interfaced, and this CRT is the image tube, that is the cathode ray tube. Now let us discuss how an image formed in a SEM. So as evident from this figure, we have an electron beam which is coupled through the detector, and an amplifier is amplifying this signal, and using this cathode ray tube, it is focused onto the specimen. So beam is scanned over the specimen in a raster pattern in synchronization with the beam in CRT. So intensity at A on CRT is proportional to the signal detected from A. This is the A point, which is given in red color, on the specimen, and this signal is modulated by an amplifier. Now let us compare the OM, optical microscopy, TEM and SEM. So these three figures compares the optical light microscope, which shows their principal features, the transmission electron microscope, and lastly the scanning electron microscope. Now the electron beam source for the scanning electron microscopy, the basic phenomena behind that is thermionic or field emission, and the thing which is used to produce the electron beam is the thermionic or field emission gun. So here we have the single crystal LaB6, which is heated using a heating cup, and then it is transferred to the heating wire, which may be tungsten or ruthenium. So let us now first discuss the thermionic emission gun. So this is the figure which is showing the schematic of a thermionic emission gun, where it uses a tungsten filament which is heated by DC to approximately 2700 Kelvin, or LaB6 rod heated to around 2000 Kelvin. Now all these things, they are placed in a vacuum of 10 to the power minus 3 Pascal or 10 to the power minus 4 Pascal for LaB6, which is needed to prevent the oxidation of the filament. So electrons, they boils off from the tip of the filament, and now these electrons, they are accelerated by an acceleration voltage of around 1 to 50 kilovolts. So students, let us discuss the next type of emission gun, that is field emission gun. Now as you can see in this figure, the tip of the tungsten needle is made very sharp, that is its radius is less than 0.1 micrometer, and the electric field at the tip is very strong, greater than 10 to the power 7 volts per centimeter, due to the sharp point effect. Now here the electrons, they are pulled out from the tip by the strong electric field. Now, a ultra high vacuum better than 10 to the power minus 6 Pascal is needed to avoid the ion bombardment to the tip from the residual gases. So, electron probe diameter less than 1 nanometer is possible in this case. Now, let us compare the source of electrons, that is from thermionic gun and from the field emission gun. In the case of thermionic gun, it can use the tungsten and LaB6 filament, and in the case of field emission gun, it uses a tungsten filament. So, this table tabulates the electron gun properties. That is, if we are using the TFEG or CFEG, it has the maximum brightness and the stability is very high. But in the case of tungsten and LaB6, it has the stability of around 50 micrometer and 5 micrometer respectively, and the size energy spread vacuum is around 3 electron volt for 10 to the power minus 5 Pascal. Now here brightness, it represents the beam current density per unit solid angle. Now we have two types of magnetic lenses, a condenser lens which is used for focusing, that is, it determines the beam current which impinges on the sample. The second is the objective lens which is used for final probe forming, that is, it determines the final spot size of the electron beam and determines the resolution of a SEM. So, what is the reason? The need of a vacuum. When a SEM is used, the electron optical column and sample chamber must always be at vacuum. First reason is that if the column is in a gas-filled environment, then electrons will be scattered by gas molecules, which would lead to the reduction of the beam intensity and stability. Second reason is that the other gas molecules which could come from the sample or the microscope itself could form compounds and condenses on the sample. This would lower the contrast and obscure the detail in the images. So let us discuss the condenser lens in detail. That is, this is the figure showing the schematic of a condenser lens. For a thermionic gun, the diameter of the first crossover point is around 20 to 50 microns. So, if we want to focus the beam to a size less than 10 nanometer on the specimen surface, the magnification should be around 1 by 5000, which is not easily attained with one lens, say the objective lens only. Therefore, condenser lenses are added to demagnify the crossover points, and this demagnification is equal to M equal to F by L, where F is the distance between the crossover point and the condenser lens, and L is the distance between the two condenser lenses. So students, let us now discuss about the objective lens. The objective lens controls the final focus of the electron beam by changing the magnetic field strength. The crossover image is finally demagnified to approximately 10 nanometer beam spot, which carries a beam current of approximately 10 to the power minus 9 to 10 to the power minus 12 amperes. The objective lens, by changing the current of it, the magnetic field strength changes, and therefore the focal length of the objective lens changed, as shown in this figure. The scan coil and raster pattern. So here we have two sets of coils which are used for scanning the electron beam across the specimen surface in a raster pattern similar to that on a TV screen. So as you can see over here, this continuous line shows a horizontal line scan, and this dashed line shows a blanking. So this effectively samples the specimen surface point by point over the scanned area. So students, let us now discuss the electron beam and specimen interactions. So we have the 6 or more different kinds of the interaction between the sample and the incident beam. So when the electron beam strikes the sample, both the photons and the electron signals are emitted. So as shown in this figure, if there is an incident beam having energy from 1 to 50 kilo electron volt, then there may be an emission of Auger electrons, which are surface sensitive and compositional information. There may be the emission of X-rays through thickness. There may be the emission of primary backscattered electrons, which may depend upon the atomic number and have the topographical information. There may be the emission of cathodoluminescence, which has the electrical information. Then secondary electrons can also be emitted having topographical information. So this gives the overview of how does the electron beam interacts with the specimen. Now let us discuss the secondary electrons. That is, this figure shows how the secondary electrons are produced. So secondary electrons, they are produced by inelastic interactions of high energy electrons with the valence or conduction electrons of the atoms in the specimen, causing the ejection of the electrons from the atoms. So these ejected electrons with energy less than 50 electron volt are termed as secondary electrons, and each incident electron can produce several secondary electrons. So now secondary electron yield is represented by delta, which is equal to number of secondary electrons divided by the number of electrons in the bulk, and it is independent of the atomic number Z, whereas it decreases with increasing beam energy and increases with decreasing glancing angle of incident beam. So this figure shows a SEM image of the barium titanate, and here as you can see that there is a production of secondary electrons which is very topography related. Due to their low energy, only secondary electrons that are very near the surface, that is less than 10 nanometers can exit the sample and be examined having small escape depth. So students, let us now discuss a topographical contrast. So this is the figure which is explaining in detail how a topographic contrast arises because a secondary electron generation depends upon the angle of incidence between the beam and a sample. And here the right hand side figure shows a schematic of the ejection of the secondary electrons from the photomultiplier tube, that is PMT. Backscattered electrons or BSE. Now this figure shows the emission of the backscattered electrons, that is, they are produced by elastic interactions of beam electrons with nuclei of atoms in the specimen, and they have high energy and large escape depth. This figure shows a BSE image from the flat surface of an aluminium having Z equal to 13 and a copper having Z equal to 29 alloy. So now BSE yield which is represented by eta, which is equal to NBS, that is number of backscattered electrons, divided by the electrons in the bulk, is a function of atomic number Z. So BSE images shows the characteristics of atomic number contrast, that is high average Z, it appears brighter than those of low voltage Z. So here eta increases with the tilt. Let us now discuss the two types of interaction volume, that is interaction volume first and interaction volume second. So on the left hand side figure, which schematically represents the interaction volume first, which shows the Monte Carlo simulations of 100 electron trajectories where the incident electrons, they do not go along a straight line, but they go in a zigzag pattern inside the specimen. Now on the right hand side, we have interaction volume 2, that is the penetration, or more precisely the interaction volume depends on the acceleration voltage, which means the energy of the electron, and the atomic number of the specimen. So here you can see that how the surface of the specimen varies with the energy of the electron. So this explains the electron interaction volume, where this figure shows or illustrates how the electron beam interaction in nickel. So electron interaction volume in polymethyl methacrylate, that is a plastic having a low Z matrix, is indirectly revealed by etching. So let us now discuss the magnification in the case of SEM images. Now these two are the two images. The left hand side shows a low magnification as large as 40 microns, and the right side figure shows a high magnification which is small as 7 microns. So basically we can say the magnification is simply the ratio of the length of the scan C on the cathode ray tube CRT to the length of the scan X on the specimen. So for a CRT screen that is a 10 centimeter square, we have M equal to 10 centimeter by X. So increasing M is achieved by decreasing X. So if we want to have M to be 100, we should have X as 1 mm, and if we want to have M to be 100K, then X should be reduced to as low as 1 micron. Resolution limitations. Ultimate resolution obtainable in a SEM image can be limited by, first, the electron optical limitations, that is diffraction d equal to 1.22 lambda divided by alpha. For a 20 keV beam, lambda equal to 0.0087 nanometers and alpha equal to 5 multiplied by 10 to the power minus 3, whereas d is equal to 2.1 nanometers. Chromatic and spherical aberrations d minimum equal to 1.29 lambda to the power 4 multiplied by Cs to the power 1 by 4. So a SEM fitted with an effigy, it has an achievable resolution of around 1 nanometer at 30 kV due to smaller Cs, approximately 200 nanometers, and lambda. So the specimen contrast limitations are, we have a contrast 1 corresponding to Dmin equal to 2.3 nanometers, contrast is 0.5, Dmin is 4.6 nanometers, contrast is 0.1, Dmin is 23 nanometers. If the contrast is 0.01, then Dmin is 230 nanometers. So sampling volume limitations escape the volume. So students, let us summarize what we have learnt in this module. Firstly, the advantages of SEM over the optical microscopy OM were explained. Second, the different electron beam sources like thermionic and field emission gun have been described. Thirdly, the importance of condenser lens, focusing, and the objective lens, which is a final probe forming in the resolution of a SEM, is illustrated. Lastly, we discussed about the interaction between the electron beam and the specimen by explaining about the topological contrast, backscattered electrons, and electron interaction volume. Thank you.